Alright, thanks for watching and congratulations for making it this far. Today is the last lecture of our vector calculus extravaganza, and we're gonna end it with the bang by using Stokes Theorem, which is the quintessential vector calculus FTC theorem. So what does Stokes Theorem say? Suppose you have a surface S. So think of S as a balloon, and it has a boundary curve C. So maybe something like that. And assume C, respects the boundary of the orientation of the surface. And by the way I like to think about this is S as being the balloon, and C is like the string at the end of the balloon. So then, what does Stokes' theorem say? It simply says that the double integral of the curl of f dotted with ds is equal to the line integral of f dotted with dr. In other words, Stokes' theorem transforms a very complicated surface integral into a much easier line integral. And vice versa. It also transforms a very complicated line integral into actually an easier surface integral, which is the point of view we'll use today. And I'll explain also the intuition behind it, and hopefully by the end it should make sense. But just one thing though, the way to think about this is simply Stokes' theorem tells you that the double integral of the derivative of f equals to the integral of f. So it's like a fancy version of the fundamental theorem of calculus. Okay, and as I said, there are two applications of this. First of all, it allows us to calculate double integrals of curls, which is pretty complicated. It also allows us to simplify line integrals. So in fact, let's now calculate the line integral of f dr, where f is this very complicated vector field. So not only is the vector field pretty complicated, but also C is pretty complicated. C is the curve of intersection of the plane z equals to y plus 2, and the cylinder x squared plus y squared equals to 1. So let's first of all draw what this looks like. So x, y, z. And on the one hand we have the cylinder. And let me use some more colors. That's x squared plus y squared equals to 1. On the other hand, we have the plane. And usually those kinds of planes are easier to be drawn with intercepts. So the z-intercept becomes 2, and the y-intercept is minus 2. So it looks something like that, except it doesn't depend on x, which means we can just shift it with respect to x. So z equals to y plus 2 looks like that. And essentially what you have to think of is simply you taking this can, this cylinder, and you slice it diagonally. So if you actually do that, you'll see that the curve of intersection is an ellipse. It's a diagonal ellipse. Okay, that's the first thing. Draw a picture, see what's going on. Now, the next thing is simply to find an S. So, find S. And remember this picture I just erased? We had this boundary curve C. And the point is, for S, we can pick whatever we want. As long as the boundary curve is the same, we always get the same answer. This is the cool thing about Stokes' theorem. In particular, let S be the easiest thing possible. In this case, given the curve C, let S just be the flat inside of that curve. In other words, what does that mean? Let S be the portion of the plane, z equals to y plus 2, over the disk x squared plus y squared equals to 1. So, or less than or equal to 1. So, let S be the portion of z equals to y plus 2 over the disk x squared plus y squared less than or equal to 1. Again, the point is, as long as the boundary curve is the same, you still get the same answer. And now what you want to use is, of course, Stokes Theorem. Stokes Theorem, which says that the line integral of f dotted with the r, which, by the way, it's possible to do it directly, but it's a pain. Because you have to parametrize this curve, and also you have to plug in the values of f. It's not fun. What is more fun, though, is to calculate the surface integral. So curl of f dotted with ds. Now, what is the curl? It's simply the the cross product of the derivatives and the vector field. So let me do that. It's essentially a number, a vector, which gives you the rotation of f in each direction. So curl of f, that is the determinant of ijk, partial over partial x, partial over partial y, partial over partial z of our vector field. So 2y, xz, x plus y. And that becomes, so, the x derivative of x plus y, messing things up. So boom, you take the y derivative, so partial over partial y, x plus y, minus partial over partial z, xz. Then you do the second thing now. Partial over partial x, x plus y, minus partial over partial z, 2y, but with a minus because of determinants. So minus partial over partial x, x plus y, plus partial over partial z, 2y, and lastly, like cross product, partial over partial x, xz, minus partial over partial y, 2y. Minus partial over partial y, 2y. Okay, and basically you get 1 minus x. Now, minus 1 plus 0. So minus 1. And lastly, z minus 2. And you see, this is already much easier than 2y, xz, and x plus y. So even though we have to do a surface integral, it's a much easier surface integral. Okay. And now remember how to surface integrate. You have to parameterize stuff. So again, this is your surface S. Okay, and it turns out here it's slightly easier. S is the graph of a function, and there is a different formula for it, but I hate that formula, so let's just do it from principles. Again, what is S? Is the part of the plane z equals to y plus 2 over the disk x squared plus y squared less than or equal to 1. So because it's a graph, it's easier just to choose parameterization rxy, where xy is here. So our x is basically x, y equals to y. So x equals to x, y equals to y, and what is z? Is just y plus 2. In other words, r of xy is xy, y plus 2, subject to x squared plus y squared less than or equal to 1. That's your parametrization. The second thing is simply finding the normal vector. So Rx is 1, 0, 0. Ry is 0, 1, 1. Cross it. Whoa, 2 cross products in one problem. How exciting. So ijk 1, 0, 0, 0, 1, 1. If you do that, you get the 0, and then the 1, 1, so minus 1, and the 1. And here's just one little thing. You always have to make sure that the normal vector, again, respects the orientation of your curve, so for your surface. Because notice, by convention, C is counterclockwise, and then if you use the right-hand rule, you notice that the normal vector has to point upwards. So make sure whatever normal vector you have in this case points upwards. And indeed, it does, because the last component is positive. So good. Upwards. And lastly, now we have everything. Let's calculate our surface integral. So double integral of S, curl of F, dotted with ds. That is double integral of D of, remember the curl was 1 minus x minus 1 z minus 2. So x is still x, minus 1 is minus 1, but remember z is y plus 2. So you get y plus 2 minus 2 dotted with your normal vector 0 minus 1 1, and again dx dy. Those two cancel out, and then if you dot it, you get 1 minus x times 0, minus 1 times minus 1, which is 1, and y times 1, which is y. So the point is, in the end, it's much easier to calculate that integral. And so you get double integral over d of 1 plus y dx dy. How much easier is that? All we have to do is just calculate this double integral. And for this, remember, d in this case is just a disk of radius 1. So it's the perfect time to use polar coordinates. Let's see if this works. Yeah, sort of. Integral from 0 to 1, 0 to 2 pi, 1 plus r sine theta. r dr d theta. That's equal integral from 0 to 2 pi, integral from 0 to 1 of r plus r squared sine theta dr d theta. Now, for this part, well, r doesn't depend on theta, so we have 2 pi, and then if you calculate the antiderivative, it's r squared over 2 from 0 to 1. And here the interesting thing is, the integral from 0 to 2 pi of sine of theta just becomes 0. So arrivederci, this goes down, and you're left with 2 pi times 1/2, which is pi again. So you see, well, I want to see no messy calculations. No messy calculations, really. It's just a bit long, that's all. But again, the alternative would be really to calculate the line integral, which is pretty messy. All right, last but not least, before we end this, let me give you some intuition behind this. Because I'm claiming that Stokes' theorem is just a surface version of Green's theorem. Remember what Green's theorem said. It says that, right, the line integral of f, it's in 2 dimensions, f dr equals to the double integral of quixotic Peyams, x dy. And the interpretation of this was, again, the global circulation of f around C is just the sum of those little circulations, qx minus py. So, in other words, if you sum up those mini hurricanes, you should get the big hurricane. It turns out we have the same thing here. Suppose you have a surface. So we have a surface, and the boundary curve is C. Then what does Stokes' theorem say? It says that the global circulation around that surface equals to the double integral of curl of f dotted with ds. And what is the curl? It's a vector which measures the mini circulation, namely the rotation of f in the xy, xz, and yz directions. So it's still the same picture. You have those mini circulations here. In other words, those mini circulation vectors. And Stokes' theorem says that if you sum up those mini circulations on the surface, you get the global circulation on the curve. So it is really like a surface version of Green's theorem. Green's theorem works for this flat 2D surface versus Stokes' theorem works for this curly surface, if you like. So it's the same thing, but both are very useful ways of calculating line integrals, except Green's theorem is for 2 dimensions, Stokes' theorem is for 3 and higher dimensions. All right, and this officially ends our vector calculus extravaganza. I hope you had a good time, and if you're taking my class, good luck on the final. I'm counting on you. And yeah, so if you like more math and want to see more extravaganzas, please make sure to subscribe to my channel. Thank you very much. Woo!